Uh, Thank you all for being here today. Good afternoon. And the topic has already been introduced. I'll be presenting my work to you on analyzing singing voice expressivity with a focus on singing voice musical dynamics. So first, I would like to express my gratitude to my supervisor, Shabir Serra, for giving me the opportunity to work on a topic that's so dear to me. And I would like to extend my thanks to the jury members for taking the time to read through the dissertation and being here. Now, let me walk through my research. So, expressivity. In the context of MIR, multiple definitions exist on expressivity. For our scope, we use the one defined by Fabian and Leach, who say expressivity is variations or deviations from a prototypical performance in terms of timing, intensity, or dynamics, pitch, timbre, tempo, articulation, or irregularity in one or more acoustic dimensions like pitch, amplitude, or duration. Now, let's narrow our focus to expressivity in the singing voice using an example. Ellen's Gesang 1, this is a piece by Schubert, and this composition was written in the context of a war, and the lyrics include the word Schrecken, which mean terror or shock at witnessing war. Now, let's listen to different performers and hear how they interpret this moment of the piece to convey this emotion. First, by Jesse Norman. Ellie Ameling. Gundula. So we notice that each performer uses different tools of expressivity. There is timbre, there is articulation, there is phrasing, there's vibrato, there's an ornament there, the number of things that are happening. We hear Gundula is playing around with the timing, but one particularly striking feature expressive dimension that you hear is loudness variation, which you probably heard when listening to Jessie Norman and Ellie Ameling. So Jessie Norman chooses to soften her voice to convey the emotion, while Ellie Ameling uses the opposite approach, intensifying the moment through increased loudness. When it comes to singing voice, expressivity, of course, it has been explored from multiple angles. For example, in MIR, it has been studied from timbre and vocal technique perspective. However, dynamics have received far less attention in the MIR field. This leads us to the focus of my thesis and this presentation, musical dynamics. We define musical dynamics as loudness or intensity of a performance, representing the sound levels as intended by the composer or interpreted by the performer. And in this thesis, we focus on the dynamic categories ranging from pianissimo to fortissimo. In Western music, dynamics have been formalized using notated terms, which the musicians in the room are perhaps already familiar. It's piano, pianissimo, crescendo, diminuendo, and so on. So what our goal is to quantize vocal dynamics using this established score vocabulary. Or more formally, given an unknown recording, we would like to segment it in terms of dynamic boundaries. We're going to approach it through different use cases or tasks. And before going into the task definition, I would like to exemplify some of the contexts or tasks. So this is a composition-driven expressive indication, which again, the musicians in the room might be familiar that you first expect an increase in loudness followed by a decrease in loudness. Let's hear how the performers play this piece. Ellie Ameling. Gundula. So we can clearly hear that the performers follow or respect the dynamic markings that are provided by the composer. Now let's take another context, which is a performance-driven expressivity. In most of modern music and also many music traditions where score is not much relevant and there might not be many expressive indications, learning happens through imitation. So performers also imitate expressivity and in particular dynamics. So let's take an example again. This is
Run, run, lost boy, they say to me, away from all of reality.
Now let's hear how a professional imitator imitates the performance.
Run, run, lost boy, they say to me, away from all of reality.
So we could clearly hear that the dynamic variations were preserved during the imitation process. Now, if we create a score of the previous example and ask different annotators to annotate the score with dynamic markings, this is what we obtain. So in this example, dynamics markings are not part of the score, but there's a tradition that when a teacher teaches or a musician hears a performance, there's an interpretation of what the performer did, and that interpretation changes depending on the musician who is hearing the performance. And there is agreement, but not precise agreement here. So having seen all of these examples, what you saw was there was an audio performance, there was a score, and what we would like to do is propose methodologies to analyze and quantify dynamics both from audio performance and from scores. So we take a step-by-step approach to the task. We could go from performance to performance. That is, given a performance, there are multiple imitations of the piece, and we could compare them. Or we could go from score to performance. So this was throughout our research as it evolved, what we found that this performance to performance comparison had limitations. So we introduced scores to have the annotations that are part of the scores. And while we were working with scores and we are thinking of the task of quantifying dynamics, we see that there is another layer of complexity, which is to do with the subjectivity. So what we saw in the previous example, that the annotations are, they have their own interpretation, and they might not be that precise. So this brings me to the structure of the presentation. I'll begin by outlining different research tasks which are organized around the three main approaches that we identified earlier. The tasks include comparative analysis of audio performances, automatic estimation of performance-related labels from scores, and analysis of listener agreement on perceived dynamics. I want to also highlight here that in order to study each of these approaches effectively, we needed to curate a number of data sets. It's a limitation. So dataset curation is an integral part of the research process, and I'll be discussing it alongside the research tasks. I'll also provide a summary of the data sets that we created towards the end, and in addition, I'll briefly present an experiment we conducted with Hindustani music before wrapping up with the conclusions, key contributions, and future directions of this work. So I'll start with the first task, which is to do with the comparative musical dynamics analysis using audio performances. And in this case, we are going from performance to performance. So if we have multiple imitations of a performance, we would like to analyze the variations between those audio performances. So here I would just like to briefly mention that when we started, one of the major aim for this work was to try and support music education platforms, and hence music education was an important context. That is, how to give feedback to the performances was the starting point. So what we noticed was that several music education applications like Musician, Cortosia, Riaz, they provide feedback on dimensions such as pitch and rhythm, but they do not offer feedback on expressive aspects of the performance. And given this gap, we focused on analyzing dynamics. And to provide feedback, this is how we approach it. We have a student recording, we have a reference recording, we carry out feature extraction for both the performances. We can do a performance level measurement, and that can be used to give feedback. But the data that we have is all polyphonic in the real world. So this led us to two research questions that we wanted to address as part of this initial investigation. The first being, given a mix, is it possible to extract a clean vocal signal that can be used for dynamics extraction? And second, can we analyze the similarities and differences between two loudness curves in order to understand dynamics? We had to, as I mentioned earlier, we have to curate the data sources for each of the approaches. So for doing performance-to-performance level analysis, we curate a dataset for commercial, from YouTube, we collect commercial official recordings of some rock and pop songs. And for those identified songs, we found some karaoke tracks. And these tracks, they imitate the performances quite well, basically. So these are professional renditions of the commercial tracks. And for the same tracks, we also, at the time, since, as I said, the context was music education, so we had the data set from Smule web application, and we applied some processing to filter out some data from that, and we had kind of, let's say, student recordings, or well, their data set from an edutainment perspective. Okay, so this was the methodology that we followed for dynamics analysis. So this methodology was actually motivated by Katerina's work, so which involved computing loudness curves for piano recordings. So we aim to extend the analysis to singing voice and focusing on musical dynamics. So I'll explain the methodology in detail for each of the performance. So this shows the performance, we're comparing two loudness curves. So for each part, at the time, basically, since I mentioned earlier, the data that's available to us is polyphonic. So we could use the existing source separation algorithms, and we wanted to see if they were suitable for our task or not, for dynamics analysis. So at the time, splitter had become quite known, and we wanted to test it out for our experiment as well. So we get the isolated vocals using splitter, followed by loudness extraction using SON, which is again motivated by Katerina's work, and it offers a linear mapping to perceived loudness. And once we had the loudness curve, we smoothen out the loudness values to obtain a continuous loudness curves. And ideally, from this curve, what we would like is to get the dynamics indicators. Okay, so let's look at it from an example. We have a reference recording, and at the bottom you see a version by Nora Jones. So this is the source separated version. So I'll be playing only a snippet of it. What you see here is the whole curve, but I'll just play a snippet to show how source separation sounds like.
I waited till I saw the sun. I don't know why I didn't come.
Let's look at the professional imitation.
I waited till I saw the sun. I don't know why I didn't come. I waited till I saw the sun. I don't know why.
Okay, so what you saw basically, there is some kind of structural similarity between the songs. So in the professional imitation, we see that the correlation values of these two loudness curves is quite high. And so we extended the analysis with some other songs from commercial recordings, and we found that the correlation values using these loudness curves were reasonably good, and we could use that as a starting point for dynamics analysis. And we also wanted to see if source separation could be used as a pre-processing step. So if we compute the mean of the values of the source separated version from the stem tracks that we obtained from the karaoke website, and we use the stems and compute the correlation with the reference renditions, these are the mean values. Well, the point is that they're not that different, and we could use state-of-the-art source separation algorithms for dynamics analysis. We also did the analysis using another data set, using the MuseDB data set. And again, we had the stem tracks, and we could do the source separation. And we found that of 149 tracks, 138 songs had correlation values greater than 0.9. And we proceeded forward to say that perhaps we could use it as a starting point for dynamics analysis. Okay, so here we ran into challenges. Ideally, in the processing, the idea was that at the end, we should be able to get the dynamics labels corresponding to the loudness curves. But now we have this whole curve, and it's not possible to map the peak values to the dynamics labels. We don't know a clear boundary. At what point do we segment? So there were now multiple approaches to address this problem. We could either work with musicians to collect labels, or we could use perhaps artificial synthetic data in which we can modify the loudness values and basically use artificial data as well. So we tested out with all the approaches. Here it gives just a summary of all the approaches that we took. I mean, it's the focal point is that for the songs, we started working with music teachers. We started creating scores, and we're using a synthesizer. So at the time, we also were collaborating with Voctro Labs that could give us the synthetic output for the scores that we created. So we wanted to test with that approach, how the synthesizer sounds. And we also, since we were creating the scores, we were at the time also working with musicians to get the labels for those scores. At the same time, we were trying to improve the evaluation for dynamics analysis, which was based on change points, that perhaps instead of comparing the whole loudness curve, we could just use the change points. Change points, I mean, where the dynamics change within the course of the performance. So now as I said, we tried to experiment with all the approaches. The part of using the synthesizer that was in collaboration with Voctro Labs, we had the score, we created the score manually, and we used the Vocaloid to synthesize, and let's hear what it sounds like.
I met you in the dark, you lit me up, you made me feel as though I was in.
And let's hear the professional imitation.
I met you in the dark, you lit me up, you made me feel.
Okay, there's lots of echo there. So you all must have probably heard the synthesizer did not have the dynamics. So this is what it looks like. For a professional imitation, the variation in dynamics is quite visible here. And this was the loudness curve. So we were testing with this approach, we were using synthetic data and it's comparing with the loudness curve. And for the synthetic data, it looks very flat. If we change the dynamics labels in the score to forte, fortissimo, whatever the label, we don't reach significant dynamics changes. And computationally, these are the results that we obtained. So I also introduced at the beginning the student data, which was with the Smule web application. So for all the student recordings that were useful for our task, if we compute the mean of the loudness curves, again with the student renditions with, alongside the reference rendition, so we found that the student renditions, which perhaps had several inaccuracies, they scored better than synthetic data, and obviously professional renditions are the best correlation values. So this was the summary of this part of the exploration, performance to performance analysis. So the idea is measurement of dynamics. It can be quantized to some extent using loudness curves, and source separation can be used as a starting point for dynamics analysis. And there were a number of problems. Some of them I highlighted before, and there were other problems like compression in pop singing is quite high, so the dynamic range is quite low, and that was another direction of exploration. But of all the problems, what we decided to focus was real data. So we wanted to curate real life score performance data. So that led us to the second approach, and just to stop for the first approach, the publication, we had publications at CMMR, DAFX, and ISMIR LBD showing these approaches. And since we didn't have real-life score performance data, we switched to the next task, which is automatic estimation of singing voice musical dynamics, in which we're actually going from score to performance. And since we focused on the point, as I said, we don't have the labels, so we can use the labels from Western classical scores and map them to performances to get performance labels. So that becomes our task. So we frame it as a machine learning problem, and the idea is to carry out classification of audio frames into categories ranging from pianissimo to fortissimo, and the core part of this task was to collect labels from scores and map them to performances. So there is lack of annotated dataset with rich dynamics. That's the challenge. So we propose learning from score performance pairs with the scores parsed automatically and performances from YouTube. So here, drawing inspiration from the notion that songs from the 19th century Romantic era are rich and expressive parameters, we leverage the open score leader corpus, which provides XML format scores with valuable metadata such as composer, performance names, and their MuseScore IDs. I'll be giving an example in a bit for this part. And for testing, we manually worked with, we curated the labels manually in collaboration with a classical vocalist, and that data set also it's of diverse genres, and it's very rich in dynamics. This provides score performance mapping. So what we had originally from MuseScore, we could get the composer information, we could get the piece information, and that information we could use to search for performances from YouTube. That also we have to do it manually because it's difficult to automate this process. And it looks something like this. We collect the YouTube IDs, we collect the player, an example of which you heard early on, and the gender information. So we manually curated about 970 performance links using these searches. This provides a snippet of the test data set. I don't know what that is. No. Okay, so for the test data set for curating the problem was we first needed to identify the songs that were rich in dynamics. So in collaboration with the classical vocalist, we first identified the songs, and then creating the scores is also not as straightforward. We listen to the performance, and then we see whatever sources we are using, the scores are usually wrong, and then we correct them manually, and finally listen to the recordings multiple times to get the right dynamics markings. So this again was in collaboration with the classical vocalist, and there were songs from multiple genres, including rock, pop, theater, jazz, soul, so on. So this shows the distribution of the data that we collected. We had about 163 score files, and we had 25 testing data, manually curated files, and it shows the label distribution here, and this shows for both the cases basically, and we notice clearly a pattern that for classical music, the labels are a lot more spread out, and for the test data, the labels follow a relatively Gaussian trend despite being rich in dynamics. And this, the right side, it shows the statistics in terms of time that we curated. I'll get back to the part of the pipeline that we followed for collection of the score performance pairs. So first, from the XML scores from the leader corpus, we carry out processing using Music 21 to obtain the dynamics labels corresponding to the vocal parts. Next, using the metadata information, we collect performances from YouTube that had piano and vocals and apply source separation to get isolated vocals using, this time we use DMUX. And finally, using automatic alignment, we obtain scores aligned with the performances. However, the resulting score performance pairs may have noisy alignment. So we have created this mapping, score performance mapping, but the resulting data might not be the one that we can use because they might not be following the score completely. So to filter out those renditions, we implemented like a debugging tool to plot the scores and performances on top of each other. So here on the right is the red dots are the fundamental frequency from the performance, and the black dots are it's converted to MIDI from the scores. So if we plot on top of each other, we clearly see that this sample we cannot use for our analysis because the performance is not in line with the score that we have from the leader corpus. And on the left is the one where the score and the performance are matching. We can use the labels that we get from the performance for the task of dynamics estimation. Okay, so this shows the pipeline. We have the training data, which consists of aligned score performance pairs. We have the scores that can be used as ground truth. Well, the ground truth is questionable, but at the moment, let's say, for the sake of simplicity, let's use them as ground truth. And then we can do feature extraction or learning to get frame level learning for dynamics. And with that, we have a model that's trained on this Western classical leader corpus. The test data, we have the aligned performances from diverse genres. We have manually created the scores with the dynamics markings that eventually we can use for evaluation. So we can use different input representations in the feature extraction to carry out evaluation for dynamics here. So this actually was, a large part of it was done by Nazif. The model here, it's inspired from the violin technique estimation. We adapted that model to do the task of dynamics estimation. So it was, if we pose it as a 10 class classification at the frame level, and we want to identify the dynamics from pianissimo to fortissimo. And we use the same network with different input representations. We tested with different input representations that I was talking about earlier. One was logmel, which is largely used in the MIR field and motivated again by our previous work where Bach features were the starting point for our analysis. We computed the Bach features using the Zwicker loudness calculation method for time varying signals, which is an ISO standard. And here we see a snippet of the results. So already we can see to some extent visually that the Bach-based features are performing better than log-mel features. And if we look at the metrics, basically it's more clear that the Bach-based features outperform log-mel features that we anticipated at the beginning. And then we also notice that if the context window is long enough to encapsulate the whole song, we obtain improved results. And we also introduce relaxed accuracy because dynamics is relatively subjective. So with relaxed accuracy, we are providing a margin of tolerance, and which is obvious in a way the results improve. And here with relaxed accuracy, we notice that there was a significant improvement in what we found. So that's the summary of this part. We introduced an expressive score performance data set along with a scalable method for its expansion. We released high quality scores with dynamics labels annotated by a professional vocal coach. We show that the Bach features outperform log-mel features for dynamics analysis, especially with longer contexts. And we find that relaxed accuracy, which allows for a margin of tolerance in dynamic label predictions, yields higher values. And this work was published at ISMIR in 2024. Okay, so now this brings me to the last part of the tasks that we identified. Here is, in one example, we saw that the labels are subjective. So we question the concept of ground truth, and we create a data set, again, for this in collaboration with multiple musicians. We study the subjectivity, and we also propose some other approaches for automatic estimation of dynamics. So here it's basically going from performance to score, and we analyze the listener agreement on perceived dynamics. So it's, again, going back to the research question, quantify dynamics, and we critically examine the notion of ground truth here by studying the subjectivity and consistency of annotations through inter-annotator agreement analysis. The approach is basically looks almost like this, except like the previous one, except this time we are working with multiple musicians. So we first create the scores manually. This is the same set of scores that we had for the the songs that we selected for the rock and pop analysis. So we create those scores. We carry out source separation to get the isolated vocals. And once we had this score performance mapped data, we share it with multiple musicians to provide us with dynamics annotations. Another data set, which is released as part of this work, we created the XML scores for the 13 reference renditions. This is from the Smule web application, basically, and we provide the annotated dynamics-based annotations by 5 different trained musicians. We also provide time-aligned score and beat information. So here, basically, because there is a lot of automatic alignment that we have used in our pre-processing. So we were testing with actually multiple alignment algorithms as well, and in one of the approaches, we used the beat-based information, and so as a result, this was created, while it provided almost similar results with just F0 based alignment as well. But we released that for our data set. These were the dynamics annotations that we identified in collaboration with the classical vocalist. There is the dynamics categories. It also has sforzando, riforzando, accents, subito, crescendo, diminuendo. And this presents the analysis of the data that we have for all the 5 trained musicians. So the first 4, we noticed that they follow a kind of a pattern. They are more Gaussian, related to each other in some way. So annotator 5 that you see here comes from a different culture. He was trained in Western pop music, but his training was in India. So it was just for analysis that they don't share exactly the same pattern of annotation, and cultural background also can play a role. We also developed a visualization to see in detail how the annotators are tied with each other. So one interesting point that we noticed here is that the instrumentalists are going more detailed as compared to the singers. And annotator 4, being a trumpet player, provides very rich annotations here. Here we wanted to see visually how the objective loudness values map to the score labels. So we get the objective values in zones from the performances, and we get the labels for those performances, and this plot shows the mean loudness values across all the dynamic categories, and we computed using Pruskel-Wallace test to see the differences in the mean frame level mean value categories across different dynamics categories, and we found the results to be statistically significant, which is a non-parametric method. Now, getting to the point of inter-annotator agreement, we saw in the visualization that some annotators can go more detailed than others. So how can we study the inter-annotator agreement here? So the core challenge was how can we compare annotations that differ in segment count and also boundary placement. We approached this through pairwise analysis, aiming to find a metric that captures boundary alignment between the annotators. And to do this, we focused on intersection points that you see here. These are the intersection points of, in this snippet, I'm using the same example, annotator 3 and annotator 4, in which we had the 5 different musicians shown together. So we only consider parts where both the annotators provide a label, discarding any missing data points. This was in line with some study on literature that we found that discarding missing points provides us similar results. And yeah, that's okay. Another point that we wanted to take advantage of is that the data is ordinal, meaning the categories have a natural order or ranking, but the spacing between them is not necessarily uniform. To account for this, we tested with the Cohen's kappa using different weighting schemes, and in particular, we used the linear and quadratic weights, which is based on square distances. In this example, like intuitively, you might think that here it's forte and this is fortissimo. So in some way, they're just differing by one count in the ordinal categorization. So it deserves a more weight. So if we use quadratic weighting, for this particular example, we obtain a Cohen's kappa of 0.7. And if we use linear weighting, we obtain a Cohen's kappa of 0.54. And that basically changes the agreement from moderate to substantial. Here we show the results for linear as well as quadratic weighting together. So with linear weighting is clearly about between moderate to substantial agreement, and with the quadratic weighting, the results change and it goes to more substantial agreement and almost touching almost perfect in the analysis. Now we experimented with another approach. One way is that we apply different weights to the categories. Another way of looking at it would be that we can compute the difference between adjacent categories, as in adjacent boundary labels. So we could just see it as going up or down. So here between MF and FF, it's a positive change. Between FF and MF, again, is a negative change, positive change, and then a negative change. So if we use the absolute values, we'll obtain, this is converted into integers already, because that's how we compute it. And with difference approach, we obtain basically a perfect correlation here. So these are the results for difference in, if we change the data from absolute to difference in consecutive values and using linear and quadratic weighting. So here for both for linear as well as quadratic weighting, the results are quite good because the data is more looking at plus and minus. One important point that I missed in the past was that annotator 5 with absolute categories does not seem to agree with the rest of the annotators, and this changes when we look at the agreement from this soft to loud categorization. So they're still able to perceive to some extent that it's going loud or soft. This shows the results for quadratic weighting using absolute dynamics categories and difference in consecutive values. So annotator 5 with that we saw earlier as well does not seem to be in agreement with absolute categorization, and the rest 4 annotators, when we compute the Cohen's kappa, seem to be in agreement. And overall, of course, one might expect the difference in consecutive values provides better results as compared to the absolute categories. And here all the annotators seem to be rich in agreement. And the instrumentalist here, the trumpet player, seems to have outperformed, seems to be in agreement with all the annotators because there's more matches with the other annotators. Finally, we also looked at if we can use structural segmentation to identify dynamics bound, like how many of the structural segments fall in line with the changes in dynamics. The hypothesis being structural segments for rock and pop genres in particular are accompanied by changes in dynamics. So we have the structural segments for rock and pop songs include verse, chorus, bridge, pre-chorus or post-chorus. And here we see that for like looking at the precision values, we see that all the annotators seem to be seeing some kind of agreement of dynamics, of structural changes with dynamics, meaning that they are, let's say, using dynamics as an indicator to show structure. And then we also tested with another, like this is basically manual segmentation. So if we compute the structure segments obtained by manual segmentation and compare it with the dynamics boundaries with a threshold of 3 seconds, this is what we see, the precision values. But the outcome, the way of the analysis is that a number of changes in structure are accompanied by dynamics changes as well. And in another approach, instead of manual segmentation, we went for automatic segmentation. If we wanted to say if we couldn't use, instead of categorizing manually, we could use some automatic ways to segment, and we see that to some extent it could be. This was based on automatic structural segmentation approach using self-similarity matrices and getting the peak values from the novelty curve. So of course it's not as comparable for any of the annotators as compared to manual segmentation, but it shows some starting point that you could use structure to inform dynamics. So that's the summary of this part. We created high-quality scores with dynamics labeled by multiple trained musicians. We developed a methodology to study consistency of dynamics-based annotations and also inter-annotator agreement. And despite the inherent subjectivity of musical dynamics, annotators broadly agreed on classifying dynamics into soft, medium, and loud categories. And we see the dynamics often align with structural segments in songs. And this work is still in review. We have submitted it to JNMR conference journal, JNMR journal. The last bit is we wanted to use the methodology to study for a tradition that's nowhere close to Western music. So we wanted to use the methodology and apply it for the case of Hindustani music. So here, like the idea was that the dynamics changes do exist in Hindustani music, but it follows completely a different form of execution. For I mean to say in Western music, you have a form like A, B, A, and it might not have the same duration. Like some verse might have a different duration as compared to the other part of the structure. In Indian music, the concept is a bit different. Everything is structured around a tal cycle, and the tal is a structure in itself. So this here we provide an example of one tal cycle. It's called ek tal, and these are the terms like that are used to indicate this tal cycle. But the point here is there are 12 beats here in this tal cycle, and the entire composition is made thinking this tal cycle in mind. So I would want to, like, this led us basically to two research questions. One was that can we use the methodology that we saw with the loudness curves to study the dynamics variations in Hindustani music, like over the course of the performance, how the dynamics change. And the other part being that when I say about the tal cycle, there is a correlation of the beats with the dynamics. So we wanted to see how the dynamics change over the course within those tal cycles. So those 12 beats, within them, how do the dynamics change? So this example recording was provided by my teacher, Shubham Modi. This is for Rag Megh, and this composition is done in ek tal, and I would encourage you to listen to the beat 1 as I play this piece.
उमड़ घुमड़ घन गरज उमड़ घुमड़ घन गरज उमड़ घुमड़ घन गरज उमड़ घुमड़ घन गरज कारे कारे बदरान राय उमड़ घुमड़ घन गरज उमड़ घुमड़ घन गरज कारे कारे बदरान राय.
Okay, well, apart from the sound quality, it's very difficult to pay attention to the beats that are being played, but the entire composition was in these 12 beats. And looking at the analysis, here we show the smoothened loudness over the course of the performance, and in the second plot we see the loudness within the cycle. So what we observe in this is that the dynamics, they do exist in the performance clearly, but for this composition, it's changing from in the center somewhere. So it's going like ghumada ghumada gana gar, and then it's going softer. So at the center of the composition, it goes louder and then it goes softer. So it's also evident from the mean and standard deviation plot. Now we extend the analysis, because one example, of course, is not enough to conclude anything. So we look at the smoothened loudness plot for another composition. This is from the Saraga dataset, and this shows the overall loudness for the course of the performance. And the second plot shows the loudness variations within the tal cycle. So this tal cycle has 16 beats, unlike the 12 beats with the previous one. And here the dynamics variations, they exist clearly as evident from the mean and standard deviation, but they're not exactly tied with the beats in the same way as the previous composition. So basically, the correlation of dynamics with tal cycle clearly is evident from the variation in mean in standard deviation, but the examples are not very conclusive at the moment and needs further study. And this work was published as the FRSM conference. So to conclude, our aim was basically, can we quantize dynamics? And we took 3 approaches. One was performance to performance. We say loudness for the performance to performance. It was more of a starting point, and we concluded that, okay, loudness can be used as a starting point for feature analysis. We further used the scores and we trained a model using the same features, and we see that the model is able to, again, predict the dynamics categories broadly, as evident from the relaxed accuracy metric. And despite the inherent subjectivity of musical dynamics, we saw in the inter-annotator agreement that the annotators broadly agreed on classifying dynamics into soft, medium, and loud categories. And these are the contributions with each chapter. For the first chapter, in which we saw the analysis of variations between audio performances, we developed a methodology to study dynamics using loudness curves, and we curated a data set to do comparative performance analysis. I'll be giving a summary of the data set in a bit. For the second task, in which we went from score to performances, we introduced a method for curating score performance data set from real-world performances. We saw that the Bach-based features outperform log-mel features for dynamics analysis, especially with longer contexts, and we adapted a deep learning model for dynamics estimation. The dataset contribution, which has been a significant part of this entire work, is we introduced an expressive score performance dataset derived from the leader corpus. We release high-quality scores with dynamics labeled by a professional vocal coach. And then we, for the last part, alongside the data set, which is Sing with Dynamics, we developed a methodology to study the consistency of dynamics-based annotations and evaluate inter-annotator agreement. And we found that the dynamics often align with structural segments. This, again, is the high-quality scores labeled by multiple trained musicians. This provides us the summary of the data set. I wanted to introduce the data set first as tied to the research task, and then put it all together because it doesn't create that clarity. So here, the 2 data sets, Sing with expressions, it consists of 509 performances. So the manually curated mappings had 970. Of that, we had 509 performances for 163 unique score files. We have the test data set, 25 manually curated scores annotated by a professional classical vocalist. And the Sing with Dynamics, in which we analyze the listener agreement on perceived dynamics, we provide 65 scores annotated by 5 different musicians. For the comparative audio performance analysis, this was basically sourced from multiple places. One was the student recordings. The student recordings are the ones from the edutainment perspective. Originally, we had 24K recordings, and we filtered them out to have 5K recordings. Alongside, we have, for the reference songs, we curated the karaoke professional renditions, the synthetic renditions as well. All of this data is public. Well, not the first data, the one for which comparative audio performance analysis, it's too big to put it on anywhere. And the rest of the data set is publicly available on these repos. There's another data set contribution that we didn't use for our task, but it's still quite useful. While we were working with the classical vocalist, and collaborating with Voctro Labs, they provided us with the scores and synthetic performances. So we developed a criteria, some automatic criteria and some manual criteria. The automatic criteria was based on XML parsing, that if the songs are suitable or can be parsed with XML or not, or there were some criteria based on lyrics, that the lyrics were not completely tied to the notes properly for many scores, so the output of the synthesizer was not correct, so we discarded some scores automatically with that. And the manual criteria included listening to the synthetic performances by the classical vocalist, and she with her, yes, she filtered out some songs with incorrect diction, and some other criteria. And here we released 20 synthesized tracks, which is quite useful from a pedagogical perspective or source separation. There's a publication for that, but we didn't use it directly for our task. So getting to the point of future work, we focused intensively on dynamics at this point, but clearly there is a correlation of dynamics with timbre, so that would be the next direction, study relationship between dynamics and timbre. Another part, at this point we have focused on dynamics categorization from pianissimo to fortissimo, because a large part of it is to do with just curating data. And the future work would involve develop methodologies for other aspects like crescendo, diminuendo, accents. For the part of subjectivity analysis, we did it for performance to score. So we analyzed the subjectivity that different annotators provided from scores. But in the data set that we created, when we went from score to performances, we assumed it to be a ground truth annotation. But in the data set, we have 3 performances for like an average of 3 performances for about 163 score files. So for that, one could study the subjectivity from a score to performance standpoint, how the different performers execute the performance from score for the same score. And then extend the analysis to Hindustani music, which we saw was at the moment it needs further evaluation to say something generic about all the compositions. So that's another part. And at the end, I would like to take a moment to thank Ajay in particular, who has been there right from the beginning. He's actually almost a co-supervisor, but due to conflict with the paperwork, we could not add him officially. The other contributors for the data sets for everything are Nazif and Viviana, with Nazif also being a very close friend, the go-to person for many technical parts, and with Viviana was my go-to person for any clarifications related to Western music. And a number of other people, Seva, Michael, Tom, Pedro. Thank you, everyone. That's all. And these are the list of publications.